So I'm going to give an introduction to homomorphic encryption. My job is to give you enough background for you to follow up the following sessions. I will mainly use the BFE scheme as example. It's a simpler way of explaining homomorphic encryption. You can visualize some of the things as examples. And then after my talk will be, after lunch, you will have Yongsu's talk talking about another scheme, get into more details about how to use the homomorphic encryption. And then after that will be Kim's talk about, you can see some real code and maybe try to follow his typing, and you can write your own examples too. So let's get started. Some of the contents are already covered by Christine. I think that was like a homomorphic encryption introduction of mathematician's perspective. And here I'm trying to give you something like maybe a programmer's perspective, something, how to say, less math involved. We've been trying many years to reduce the portion of the math in explaining all these schemes, these methods. So at the beginning, so I recently got this question from the US border check. Actually, what do you work on? What's your field? I said homomorphic encryption. And apparently they say, oh, that's a horrible name. It's even hard to pronounce. You need to explain about the basic idea about this technology to him, and you can just say it's a new type of encryption, and I compute encrypted data without decryption, and no one sees the result. So it covers all the stages when you explain to the officer. A lot of you probably are from overseas or not US citizens. You might get that questions in future. And we met a lot of problem when talking to people really new to this field that they cannot distinguish encryption from hashing. The basic thing is just encryption, you can say it requires a secret key to decrypt. Without a secret key, you cannot revert it. Then they might go into more details. I passed the border at late night. So they might ask you like why people start working on this, because this wasn't available until 2009. This is a fairly new field. I was kind of lucky to get into this field in 2012. My advisor picked this new area, and that was just the beginning of this thing. And ever since 2009, we witnessed like one order of magnitude every year, kind of. Right now we have 10 to 9 times speed up compared to the first construction in 2009. And these, thanks to all the researchers and the developers from company, academia, and they will ask you, what do you work on? What does all the researchers work on? We brought up new constructions, new schemes, theoretic improvements, even optimizations on the hardware, targeting special hardwares, and we bring the slowdown down to 10 to 3 or 10 to 6. There's a slight difference, depends on how you use HE. Maybe you are a bad programmer, or if you didn't understand it well, then you get the 10 to 6 times slowdown sometimes. And the final thing is the target application scenario is HE has a killing app for online secure storage and computation. A good example is that you want to keep your DNA data secret, but you still want to use some of the services that you say find your relatives, and you can just upload the encrypted version of your DNA to the database, and they provide matching those services for you and return you the result. And even whether you have relative or not, you get some result encrypted back. Only you can see the result. Maybe someone get empty result. Maybe someone get the full list of relatives. They are all encrypted. The service provider knows nothing about it. So this is the ideal scenario, and there might be some real-life application of these. And for example, if you want to follow the IDASH computation, it spells IDASH. They focus the text on genomic data sometimes. There might be some good solutions, and there are papers to follow up. So here are just very frequent questions we got. Like say, first, we assume that there are 2 zones. One is a safe zone. It's on, let's say, when you do decryption, it requires a safe environment. For example, your laptop. That's where you hold the secret key, and it's considered safe. all the data outside this safe zone should be encrypted. I mean, encryption doesn't have to be doesn't have to be done on by yourself. It can, because there are public key encryption that use a public key, so I can do encryption for you, every one of you. But data outside that safe zone are always encrypted, even the results. And you can see, even if you compute on encrypted data and an unencrypted data, the result is still encrypted. It's like a virus. Once you get encryption there, everything will become encrypted, and which is good. And computation is never done. Like, you don't need a secret key to do encryption. Without a secret key, you cannot do decryption. That ensures the safety of your data. And there are a few popular schemes. These are the most efficient schemes nowadays. I think some of you have worked on TFHE-related schemes. They focus on logic gates on bits. It's like redesigning logic circuit. That's one scheme. And then we have BGV and BFV. They perform exact arithmetic on vectors of numbers. So first, it's better than just a single value. It's perform a vector of values, and then it gives you the exact result. You don't see any error. You don't see approximation. CKKS is a new scheme we'll introduce in the next session. It does approximate arithmetic, because at some time you don't want to keep the full precision. If you're in banking, you want to calculate the whole assets of yourself. You want to get the full precision. But what if you're doing, let's say, some floating point arithmetic? Let's say you are doing a training or inferencing, you only need maybe 8-bit precision. Then CKKS is a better choice. There's approximation involved. Microsoft Seal implements BFE and CKKS, and those two will be the ones we are going to focus on. So there are usually 5 stages in HE. You can see that in every paper covering HE. So the first one is to set up. Here I lay out everything in the order when it happens. So first thing is to set up. You need to choose the scheme. You need to choose some security parameters, and there's some performance parameters for functionality. I uploaded these slides to GitHub, so I will show you the link afterwards at lunchtime, so you can just download or look at it anytime. And probably this will apply to all the following slides in our talk, technical talks. And then after you set up the parameters, you can do the key generation. And here, this secret key is the one that you need to protect it. And the other 3 are generated from the secret key, and they are all considered public. So you can send these 3 to anyone, and they can never compromise your data. And these 2 are required for computation. This public key can be used for encryption. Secret key can be used for encryption and decryption. And then next step is to encrypt your data. So here, in a high-level view, we encrypt the vector of numbers. I'll go into more details about what the numbers look like, but just a vector of numbers, many of them, and it becomes a ciphertext, which is 2 polynomials. I'll get into that right after this slide. So we kind of want to start with encryption and evaluation stage at the beginning. Evaluation is where you really write your program. So let's say I give you a test to do evaluate the algorithm using homomorphic encryption, or let's say I just give you some simple test like a polynomial, evaluate the polynomial. You can write it down with homomorphic encryption, and this all happens in evaluation. Another way to say is it's just a computation on secure data, and this is what really matters. As you can see, it happens on the 4th stage, but we can get started here because it's more intuitive to define your algorithm, how to write the code. And at last, you decrypt your data. After computation is done, you decrypt the result. So let's get into the encryption. So I need to introduce this SIMD computation. A lot of you probably know SIMD. A lot of you don't. It's single instruction, multiple data. That means when you issue a single instruction or operation, it applies to all the data independently. So they call it single instruction, multiple data. We use that in homomorphic encryption. When you have a message, for example, the message is a vector of values, 1, 2, 3, 4, a lot of them. And there's one encoding happening here that gives you a plain text. Remember, the plain text is a polynomial. For example, encoding of 1, 2, 3, 4 can look like this. It's a polynomial. This is your plain text. I need you to remember what is message, what is plain text, and what is ciphertext. Ciphertext is the output of the encryption. So here is what security really got guaranteed. Before this encryption, everything are just plain text, like in clear state. I give you the plain text, you know the decoding algorithm, you can get it, you don't need a key. But here is where security starts to matter. And the ciphertext will have a random looking. It's totally meaningless, you don't see anything, you don't get any information from it. Suppose you're just encoding a single number, it's just become like constant polynomial. This is just 7, and still the encryption gives you a random looking polynomial. You cannot really distinguish whether you are encrypting one message or a lot of message because the ciphertexts are always random looking. And how do we do the computation? So you have 1, 2, 3, 4 encrypted. You have another 1, 2, 3, 4 encrypted. I want to do an addition. The result will be the encryption of 2, 4, 6, 8. The addition is done coefficient-wise, element-wise. Same with multiplication. It becomes 1, 4, 9, 16. So we are clear on how the computation on vectors are done here. Homomorphic encryption just preserves this addition and multiplication. So you can see we are operating on ciphertext, but the arithmetic is done on a plain text. We will get into more detail about what's the number of message slots. So a high-level idea, it is related to the degree of this polynomial. The higher degree you have more message slots. When you are having more message slots, you have more parallelism, and one operation here operates on thousands of message slots. That gives you 1,000 to 10,000 times speed up, amortized timing. And this is what matters in the last stage. When I say the performance is 10 to the 3 to 10 to the 6, that 3 orders of magnitude gap is introduced by these. You should always use these whenever possible, because otherwise you get kind of a slow program and it's not efficient. So enough on the plain text and message side, and let's talk about what are those polynomials. You need these in the following slides. We try our best to match the notations. So let's define what's the polynomial ring. We use this ring in homomorphic encryption. So it means a polynomial whose coefficients are chosen from the integers, and the polynomials are computed modulo x to n plus 1. So it means in this ring, in this R, all the polynomials have degree at most n minus 1. If you ever have a term which is x to n or x to n plus 1 or x to n plus 2, it will be reduced modulo x to n plus 1. For example, modulo reduction x to n equals to minus 1 in this ring. You just wrap around and flip the sign. So x to the n plus 1 is minus x, while x to the 2n becomes 1. So this is the basic polynomial arithmetic in the ring. And then further we have this quotient ring that's the coefficients are now computed modulo q. So your coefficients are no longer just an integer. They are represented with a set of integers. For example, let's say q equals to 5x example. Coefficients can be chosen from these 5 numbers. They are zero balanced, which is good. And the computation are done modulo 5. For example, let's say you have 2 plus 2, you get 4, but 4 is not an element of this group in this set. So 4 got related, the image of 4 becomes here is -1 in this arithmetic. So everything is done modulo 5, but you just match them into the correct element. You can also think these as from 0, 1, 2, 3, 4. You can use those 5 numbers too. Just it's not zero balanced. It might be easier to understand, but it's not zero balanced. So it's like we don't normally use that unless to do efficient programming, like writing the code. So here is a short example on the polynomial arithmetic modulo x to the n plus 1 and modulo q. So assume you have R5 and the degree n equals to 3. Here is the arithmetic. If for those of you who haven't get into this part, you can try to calculate this thing. Basically, you just multiply them term by term. You get this high degree polynomial, and you start doing reduction. Let's say x to the 4 goes to minus x, x to the 3 goes to goes to -1, but the coefficient is 0, so it's disappear. And eventually we'll get minus 5x, and modulo 5 give you 0. The end result will be just minus x squared plus 1. This is the basic way how to do polynomial multiplication and polynomial addition in RQ. We will see R and RQ a lot in the following discussion. Like if there's a multiplication, it follows these rules. If there's addition, it follows these rules. The most important parameters are n and log q. So the size of this q and the degree, those two defines your security. As Christine has mentioned that almost all the efficient schemes based on the ring learning with error problem is mathematical problem, and we try to parameterize the security level. Let's say for 128-bit security, what parameters you should choose. By parameters, we basically mean n and log q. So let's get into how the decoding and the encryption is done. First, I'm taking BFE as example, but just for you to understand how it works. So your message can have a certain form. Your message can be chosen from complex numbers, or it can be chosen from integers modulo t. T is your plaintext modulus. They say normal computer works on integers modulo 2 to the 32, which is a single word size. You can think this is just the plaintext modulus 2 to the 32 or something else. And it's a vector. It's always a vector for efficiency. What encoder does is it maps this message vector to a polynomial. If you are using BFE, which we have messages modulo t, then your plaintext will be modulo t as well. If you are using CKKS, you will have messages chosen from complex. You get just a polynomial in CKKS. They might have larger coefficients. And here the encryptor maps this plaintext polynomial into a ciphertext, which is a pair of polynomials. What it does is actually adds noise to mask the secret, which is the message or plaintext. And then it randomizes this ciphertext after in each encryption, so that encryption of the same plaintext give you different ciphertext always. Otherwise, you can read the message anyway. So this is how to make it secure. And addition, multiplication, these two operations are preserved in all three forms: message, plaintext, or ciphertext. You can do addition and multiplication on all three of them. They always preserve your computation. This is what Christine mentioned by the computation computation commutes with encryption. And what operations we can use in homomorphic encryption? The basic one is addition. So addition is simple. Since you have two ciphertexts A and B, you just add each polynomial together. Let's say you add A0 with B0, add A1 with B1, you get results C0 and C1. This is your addition result. This is how the homomorphic addition is done. And if you decrypt this message, if you decrypt this ciphertext and decode it, the message is the addition of A and B. So it's quite simple for addition. And in a case when B is a plain text, you just add B to the first part, which is even faster, just half of the complexity computation. These actually have code examples in CO. Kim will explain that later. You can see from the code that we have multiply and multiply with plain, those functions in CO that very understandable. And plain texts are computed modulo T if you are in BFV. I just want you to know that these plain text operations are not what you define. You add 1,000 with 2,000, you might not get 3,000. It's defined over this modulo T or defined in the CKKS how much precision you want to preserve. For example, if you are doing module 1001 reduction, if your T is 1001, you add 1,000 with another 1,000, you get, what do you get? 999, something like that. So remember that there's the arithmetic is not just plain addition, it's modulo addition and modulo multiplication. These grayed out stuff are just for future reference if you want to refer back to these slides. They explain the cost of these operations in terms of polynomial degree, those things. And here we also have homomorphic multiplication. It's a little bit more complicated. Multiplication actually gives you 3 polynomials as a result. You can see all A0 and B0 are used in this computation. You computed 3 parts, and this is your result. This is ciphertext times ciphertext. If B is a plain text, it's much easier. Just multiply B to both parts. That is done. You still have a 2-part polynomial, 2-part ciphertext. However, this becomes a problem when you have 3 polynomials in a ciphertext. If you want to do another multiplication, what do? There will be a lot more computation and end up with more polynomials in the new ciphertext. We don't want it to grow because when your ciphertext get larger, at the end you get like a huge result as the return result. You don't want that. So there's a step called linearization followed. This also have a function in CO. You need to call it. What it does is very simple. It just converts these 3 polynomial ciphertexts to a new ciphertext with just 2 polynomials. It's just a tool to convert it. You can think it this way. It's very simple. You just call it. It converts it back to the 2 polynomial shape. And it requires a linearization key. And this is just a public key. If this is done during public key generation, you can send it to anyone. Anyone doing the homomorphic multiplication can have this key, and we will need this key to reduce the ciphertext. So far we have 3 steps, 3 functions, and actually those are 5 functions because it also involves ciphertext plaintext multiplication. So these 5 functions should be enough for you to build a, let's say, polynomial evaluation or some basic algorithm. And in fact, most of the schemes are just built based on those 5 operations. We actually have one more. Since we are encoding a vector of numbers, you might want to rotate the slots of those numbers. Let's say I give you 1, 2, 3, 4, but you also want to have 2, 3, 4, 1, or some other kind of rotation. There's a faster way to do rotation on encrypted data. In CO, you can find functions like rotate, rotate column, rotate matrix, those functions, rotate vector. And what it does is just change the order of these slots. And it requires something called the Galois key. It's also a public key. It's like a linearization key. It's just required for the computation to be done. Anyone can have it. No security vulnerability. And as Arun mentioned in his talk, this key can be a little bit large, and you might want to consider the storage of this device That was a very interesting talk when people don't usually think about 50 megabytes public key is a problem in homomorphic encryption world because we start with gigabytes of public key. Now it's just 50 megabytes. It's super tiny. But in fact, when you are doing for example, in your computation, you need to think about real life example. You want to think about the user's case. Let's say someone has a computer offshore. You need to send a lot of data to it. You need to consider data size. And this is something to consider. Like this key can be large. And now you also have rotation. Kind of, we have the complete set of operations we have. If you're thinking about computer arithmetic, you can think that we first define addition, multiplication, and bit shifting. So based on those three, you actually have the modern computer. And here is the same. These operations, we can build very complex algorithm. Let's combine some of them and run it to code. So suppose I want to evaluate y to the 4 minus 2y squared plus 1 for this sequence, for this vector of values. What you do is, first you create a slot of n slots of 0, filled with 0, and put 1, 2, 3, 4 at the beginning. So you have y. Then you just encode y to a plaintext, encrypt plaintext y to encrypted y, and that's done with encryption. And the following, let's say I have a vector of all 2s. We have a vector of all 1s to, just to mark these two constant terms. They can be encoded to plaintext 2 and plaintext 1, so they become polynomials, and they can compute with the ciphertext y. Let's start with computation. First, you have squared y. You call this multiply to himself. So multiply y and y becomes y squared. And linearization is required because you want to reduce it from 3 polynomials to 2 polynomials. And then I want to multiply y squared with y squared, so I get y to the 4th. And also reduce the polynomial to only 2. And you multiply plaintext. So this is encrypted y is now y squared. Oh, sorry, this should be y squared. Oh, yeah, that requires some debugging. So I didn't write this code. So this should be y squared. You multiply with plain 2, you should get 2y squared. And let's say the result is stored here. And you can subtract it from y to the 4th. So here is subtracted this value from encrypted z. So in z, now you have y to the 4 minus 2y squared. And then you further add 1 to it, so you get the final result. Sure?
Will you share the slide with us?
Yeah.
And where is the parameter selection?
Later, I'll explain it later. So I'm trying to get around parameter selection because to write down this code, you don't need the parameter selection. You see, you can just write down the code with nothing. For me, I didn't even run the code. You caught me. So actually, there's a better way to do this computation. It's called, you require some circuit optimization to get a better algorithm. So both sides achieve the same thing, computation. However, the right-hand side is much simpler. You see, you have 2 less operations. We need to explain the definition of circuit here. So give you a polynomial or some function. There are many algorithms to achieve that functionality. And one of the algorithms might have the minimal depths. By depths, I mean the layer of multiplications, ciphertext multiplications. So these solid box means ciphertext multiplication. This is just ciphertext plaintext multiplication, which we don't care that much. This ciphertext multiplication is very important. We always want to minimize the maximum path of these multiplications. For example, in this graph, this is the depth 2 circuit. This is the first level. This is the second level. So you will hear the level, the depths and circuit a lot. I don't want you to get confused. This is also a depth 2 circuit, but it's simpler because you have less computation. This is some optimization that usually cannot be done by a compiler. You are responsible to write better code using these, because this requires a polynomial factorization. You need Wolfram alpha, which is not part of any compiler, right? And so far, we kind of know how to write a simple code. And what else we can do for computation? We can have linear functions, scalar, vector, matrix, addition multiplications. Those are fine, easy in homomorphic encryption. We can have polynomial evaluation. K-degree polynomial usually requires log K depth. Equality check can be tricky. There are algorithms to achieve that in BFV. It's not possible in CKKS because CKKS is approximate. You don't get kind of equal. You always want to get equal. Comparison is hard. Comparison is hard because when you're comparing -1 and 1 modulo 5, it doesn't make sense. When you're comparing 0.9999 and 0 and 1, they look similar. You don't even know whether they are equal or not. How do you know which one is larger, which one is smaller? So this comparison is kind of hard, but it's not undoable. You can approximate the result with some high-degree polynomial to achieve like approximation of the result. That technique applies to nonlinear function too. This is sigmoid, inverse, tangent, or other functions. You can always approximate these nonlinear functions with a polynomial. If any one of you has ever used the MATLAB, you have the curve fitting those things. They give you like a 7-degree polynomial to fit the curve. So you express approximation of the curve with a 7-degree polynomial, which is HE friendly. So fundamentally, HE can do all the computation, just with different cost, with different effort. So if anyone asks you that, can HE do something, or I heard that HE cannot evaluate nonlinear function, you say that's not true. And finally, we get decryption and decode. Decryption and decode, just first decryption map the pair of polynomial to a single polynomial, which is plain text, and then decode it to the vector. And there's your result. So you decrypt Z, calling these. You decode plain text Z, calling these. You get the result stored in Z. So super simple, 2 lines. How does the encryption decryption work? We can get a little bit more in detail. Basically, you generate a secret key, which is S. It's a polynomial from a ring. Then you usually secret key can be just a ternary polynomial, means the coefficients are -1, 0, or 1. They are very simple polynomials. You can read it actually. For example, we can support symmetric encryption of 0. You just generate an error. E is also a polynomial from a discrete Gaussian distribution. Is give you a random looking ciphertext. You also sample A, which is uniformly sampled from RQ. So A is modulo Q polynomial. You publish this thing. This is minus A times S plus E. Some polynomial arithmetic happening here. You get the result. And the second polynomial is just the A. So this pair of polynomial is a ciphertext. It's a symmetric encryption ciphertext of encryption of 0. We can use these as the public key. So public key and ciphertext, actually you cannot distinguish them. You should not be able to distinguish them. For example, if you want to do asymmetric encryption of 0, that means I give you the public key. I want you to encrypt something and work with my encryption. And you can do that with asymmetric encryption. What you do is you take the public key, which is 2 polynomials, pk0 and pk1. You sample a u from the same distribution here. It's a polynomial, ternary. You multiply to 2 polynomials here, and you add 2 new errors. And this is your asymmetric encryption of 0. And when you want to encrypt some true value, you just add the plain text to this part with some modification. Then you have the ciphertext and encryption of some true value. Another view is that this is your plain text. This is the mask modulo Q, for example, A times S. This part is removable with the secret key during decryption, but it's a huge noise. So horizontally, this is degree 0 to degree n, n minus 1. Vertically, this is, let's say, the least significant bit towards the most significant bit. So here you should have log q here, log q's bit. And this is the 0th bit of your coefficients. So let's assume this is a polynomial. And you can see this is like a large error. You are just masking the whole message space. All the information are randomized and masked with this thing. You also have some initial noise which is introduced with the E. These are considered small. What you do is you lift your plain text by some constant factor. Let's say this is a BFE encryption. What you do is you calculate Q over T, something close to that. Let's say your T plain text modulus can be 1,000 or a small value. The Q are usually large, a few thousand bits. You get a very large ratio here. You scale your plain text up by this ratio to raise it from the lower bits to the higher bits. And you add everything up, you get these. You can see there's a safe zone here that separates the message from the noise. And this gives you correct decryption. If you lose these, if the plain text and the initial noise kind of start overlapping, you start to lose information. In BFE, you just decryption will fail. In CKKS, you lose precisions. And along with the computation, this noise will grow. This mask is not a problem because they are always removable with the secret key, but this noise will keep growing until it eventually will destroy the safe zone. At that moment, your decryption will fail. Multiplication introduces the most noise. That's why we want to minimize the depth. Ciphertext multiplication causes a lot of noise. You want to do them like in a tree shaped rather than in a chain. Let's say if you calculate the y to the power of 4 by doing y times another y times another y times another y, you will end up with a depth 4 circuit. You will have more noise. My code might fail. The decryption might fail because the depth is much larger. However, you cannot always do things with 2 depths, so you need to have more depths. You just encrypt n and q. Once you know the depths, you should increase n and q to meet those computation need. And I will explain how to choose n and q security to meet security need. Here are just some basic terminology. You might got confused a lot of times. I'll just leave it here. You can check it online. So how to set up these security parameters? We are going back to the beginning. If you want more depth, you should increase Q because you need to draw the plain text or the ceiling away from the noise. So you increase the vertical space by increasing Q. While you're increasing, sure.
Is there a way to find the minimum Q that I need?
Usually requires some attempts. It's hard to just calculate the minimum Q. There are a lot of papers doing noise analysis. It's very hard to do. And usually the best way is just to start with a Q, try to evaluate the circuit. If it fails, increase Q. And if it fails, increase Q. That's the easiest way. And then after you decided on Q, you need to also increase N because the security definition is for a given N, the larger the Q is, the less secure the scheme is. So to make the larger Q secure, you need to increase N as well. You can always choose parameters according to Homomorphic Encryption security standard. On this link, you can find that. For example, in the table 1, you can see you have classic security, ternary secret key, 128-bit security. Suggested pairs are N is 1K and the log Q is 29. You just need to find a 29-bit Q. And these are just 4 lines to set up the security parameters. First, you choose the scheme, then you choose the degree, and you choose the default queue using seal. I mean, log Q, Q to be a power of 2. Let's say 2 to the 29, for example. You can take Q to the power of 2. You can use the power of 2, but I need to explain in the future. Next, I think a few slides more, you will see that we don't use that. So this is very easy to set up security parameters if you want to use some default parameters from seal. Well, this is a better view to choose your parameters. Let's say this n, this is log Q, the y-axis is log Q. This blue line marks the 128-bit security threshold. Above it is insecure. For certain depths or certain function, certain circuit, this brown line marks the correctness. When your Q is larger than this, you get correct decryption. You are looking for parameters from this triangle. And usually, when Q and N gets larger, the program gets more inefficient. So this is the optimal choice. How do you, according back to the questions, you probably will start with a Q here, and turns out it's not correct. You increase Q to something here, turns out it's correct, but there's a space to reduce it. Then you reduce Q to somewhere here. Okay, using the same N, you reduce Q to somewhere here. Then you get the optimal parameters. Decryption will fail. You don't get the correct decryption result.
But if you get a correct decryption result, does it ensure that every time I decrypt some other computation will be correct?
Good question. Most of the time.
I wanted to make a comment on that question. So going back to 2014, we published a paper with how to compute the correct parameters, so Q and the noise, starting from D. So if you have the depth, like if you know what you want to compute, we gave an algorithm to compute the Q and N that you should use. So you could do that, and the only problem is that algorithm uses like worst case estimates of how the noise grows. And so it'll mean that your parameters would be like an overestimate of what's necessary. And if you're really interested in performance, you might want to do a little better than that, which is, I think, why Wei is suggesting that what you could also do is just try, and increase until you get something. But if you want, going to your last question, if you want to ensure that you will get correctness and security, you can use our algorithm, and it will give you a few of the parameters.
I think you probably, using that, you can find another brown line here that gives you the guaranteed correctness, which also give you a little bit worse parameters. You can further find parameter within this ladder shape area. So I'll start explaining what's the form of Q we are using. So the previous code, you only choose a default parameter to set up the coefficients.
The parameter selection will be part of Seal's compiler?
Seal compiler?
You actually, so because like many users or many programmers, they cannot actually choose correctly these parameters. Can this part, can this whole procedure be part of Seal?
Oh, that's our plan, actually. So, for example, I think you know, and we can talk about that. We are working on a compiler that optimizes all these procedures for Seal. Focus on vector instructions. You have met Roshan, right? Roshan? Intern last year. So we've been working on that, and we can get rid of a lot of these parameter settings. Just you write your code, the compiler can work it for you. It does not get you the optimal, but in most of scenarios, it's pretty good parameters. But again, that doesn't include the polynomial factorization. So then what's the form of Q? So we need to talk about these full RNS variants. We need that in later talks. So RNS is residual number system, or like is similar to Chinese remainder theorem. Basically, you represent a large integer with a set of smaller integers. For example, if you have coprime moduli 3, 5, and 7, you can represent numbers from 0 to 124. And each one will be represented by a 3 tuple of the remainder divided by 3 of them. So for example, 8 becomes 2, 3, 1. Like module 3, module 5, module 7. 20 becomes 206. Addition are done element-wise. By doing it from here, you get 130. If you just calculate the mapping of 28, you also get 130. So this applies to addition and multiplication. By using these, we break large integer arithmetic into a set of smaller integer arithmetic and gives you a lot of speed up. And this is very important. Most of the RNS schemes are better than their original schemes. Consequently, we choose Q as a product of smaller word size prime numbers. As you can see before from these parameters, Q can be a few hundreds bits large. Computer cannot process that without like a number theory library or high precision library. But we can use RNS system to achieve that, and it's very efficient. The consequence is we need to set up QIs and P. There's also another operation here during the computation that you can discard something, a prime from that Q. So your ciphertext got smaller in terms of coefficients. It's a safe operation. You can discard some of them. Your computation gets faster. The safe zone is preserved, and is very beneficial to get better performance. And we'll need that in future like slides, in future sessions. So then how to set up the performance parameters. Before, we are just using, let's say, set coef modulus BFE default. That was the previous example. But you can do something better by giving 4 prime numbers. You can either write in 4 prime numbers here as a vector, or you can just tell the CO to create 4 prime numbers. And these 4 prime numbers have 40-bit, 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 and 50-bit. This is very simple. You just tell CO, okay, the Q size cannot be more than 220. Let's say cannot be more than 170 bit. So I choose 4 primes in total of 170 bits, and you just pass these 4 values to the function, and it creates 4 primes for you. There are some requirements. The last one needs to be largest, so that you have less worry about noise during some operations. Just always make it the largest. If you choose 4 of the same size, I remember CO will choose the largest for you to put here. So that from here, you don't need to worry about what the primes are. You just need to worry about their bit size. And this is important to use in CKKS for efficiency. This is just some basic idea. To summarize everything, let's go back to the same correct order. You start with an idea in your mind to do some algorithm and application function. You need to write it down as a circuit, HE-friendly circuit. You should think HE as new hardware rather than some encryption or arithmetic's fine. So CPU works on instructions and good at branching and integers module to the 32 or 64. GPUs are better at half precision, single precision, double precision floating points. And BFE just is good at integers modulo T or arithmetic. CKKS is good with fixed precision or truncated approximated computation. You just write your algorithm in a different way. And then you express the algorithm with these. You get the minimal depth. Based on the depth, you can choose your parameters. And there are some limitations here. Of course, you cannot do conditional branching based on the ciphertext because you don't know the ciphertext. You don't know the secret. But there's another way to achieve something similar, which is a practice question. You can solve it later. Also, these two, also nonlinear functions, or also not polynomials, they require some approximation, which will be explained in the last talk today by Hao. And then you set up the secure parameter, set up the performance parameter. This is not required if you are calling some default parameters. And then you're done with parameter settings. You will construct some classes in CO, but those are simple. You show that in demo in 2 sessions after this. And then you can define your computation. You can write down the code. When you write down the code, you need to remember that each function have different cost. Here is just a symptotic view of the cost based on the number of prime numbers you have and the degree n. You can see that multiplication is the multiplication and the linearization rotation are kind of heavy. So you might want to avoid using a lot of them. If you can get rid of one of them by introducing 2 additions, you should do that. And here are some practice problems. And you can just try to solve these questions. If you have questions, just ask me. And these slides will be available online. Actually, before that, I want to quickly show that how to measure performance parameters, performance benchmark result in CO. So I'm running a CO example. Oh, it doesn't present. Okay, so here I'm running CO examples. If you just call the 6th example, you will want to select the way to measure the performance. Let's say I want to measure CKKS with the custom degree. It asks you to type in a degree, let's say 2096. It just print out the cost. I'm measuring it on a Linux subsystem, which is not the best platform to measure performance, but you can see it gives you all the results in terms of milliseconds and microsecond. You can just use them to estimate the cost. And you can see multiplication, linearization are fairly slow compared to additions. That's everything in my talk. I hope you have a lot to process during lunchtime. And we are going a little bit over time, so let's quickly go outside to take a group picture. And then we get back to lunch. I hope you all can, sit with your teammates so that you can talk more on that. And then the afternoon session will start at 1, maybe a little bit after 1. All right.